Hello students. In this video we are going to deal with two different topics. First one is the mobility of charge carriers and second one is the conductivity of a semiconductor. So first let's start with the electrical mobility of the charge carriers. As we know that whenever an electric field is applied across a conductor, its charge carrier acquires some drift velocity because of that electric field. So this drift velocity acquired by the charge carriers when we apply unit electric field, in the case we have applied unit electric field, the velocity acquired by the charge carriers, that drift velocity is called electrical mobility of the charge carriers and it is denoted by mu. So this electrical mobility of charge carriers is denoted by mu and is defined as the drift velocity acquired by the charge carriers when unit electric field is applied. So this is known as mobility, and mathematically we can give it as mu is equal to the velocity acquired by the charge carrier per unit applied electric field. This much drift velocity is called mobility of the charge carriers in that semiconductor. Now the point here is to note that in case of electrons present in conduction band, so in conduction band the electrons are almost free, that's why they get easily accelerated by the electric field, but electrons in valence band are comparatively bound by the atoms of the semiconductor. They are less accelerated by the same electric field and acquired a drift velocity which is smaller than that of the electrons present in conduction band. So we can note it that the electrons that are present in conduction band, electrons in conduction band of semiconductor has greater mobility in comparison to the electron present in valence band of the same semiconductor. So there is a difference because in conduction band the electrons are quite free to move as compared to the valence band, because in valence band these electrons are bound to the atoms of the semiconductor. So because of that they acquire less acceleration in case of valence band while more in case of conduction band. Therefore mobility in case of conduction band electrons is more in comparison to that of valence band. This is the electrical mobility of the charge carriers and it is defined as the drift velocity acquired by the charged particles when we apply unit electric field. Now let's move to the second topic, that is the electrical conductivity of a semiconductor. So if we have a semiconducting rod material or a block of length L and area of cross section of it is capital A and it has free electron density Ne and hole density Nh. Ne is the free electron density and Nh is the hole density present in that semiconductor, and a potential difference of V is applied across its end, then the electric field set up across this conductor can be given as E is equal to V upon L, right? So E is equal to V upon L is the electric field set up across this conductor if the potential difference across its end is capital V and the length of that conductor semiconductor is L. Let it be equation number 1. Now we know that in case of semiconductors both electron and hole participate in current. So total current that we get in this case is because of the electron current as well as the hole current. So this is the value for total current. Let it be equation number 2. Now, since electron in the conduction band and holes in the valence band move randomly like free electrons, so by the relation of drift velocity, if their drift velocity in case of electron is Ve and in case of hole it is Vh, these are the drift velocity, then by using the relation of drift velocities that we have read earlier in starting chapters, we can write the value of electron current as well as hole current. So electron current can be given as E N E A V E and hole current is given as E N H A V H, right? And total current हो जाएगा इन दोनों का sum. So I is equal to E N E A V E plus E N H A V H. E is same because both have the same charge. Electron and hole has the same value of charge. The difference is of the sign only. We can take EA common and within the bracket we get NEVE plus NHVH. This is the total value of current. Let it be equation number 3rd. Now, if R is the resistance of the semiconductor and rho is its resistivity, if R is its resistance and rho is its resistivity, then we can write R as R is equal to rho L upon A. This is equation number 4. Now, we are going to analyze all these equations. So, by applying Ohm's law, the current across the semiconductor can be given as I is equal to V upon R. If we apply this relation here, we get this current I is equal to V upon rho L upon A, and V is also known equal to EL by the equation number 1. This is rho L upon A, and on solving this we get the total current I is equal to EA upon rho. The total current is EA upon rho. We can assume it equation number 5 and equate these equation 3 and 5, both are the currents. So by equating equation number 3 and 5, we get I is equal to E A N E V E plus N H V H is equal to E A upon rho, right? This is the value of current that we get by equating, and on equating these two we get E upon rho is equal to small e NEVE plus NHVH. Since we know that the mobility is equal to V upon E, so in case of electron and in case of hole, we can write this relation as mu E is equal to VE upon capital E for electrons, and for holes it is mu H is equal to VH upon capital E, or VE is equal to mu E capital E and VH is equal to mu H capital E. Now we are going to substitute these values in this equation on the place of drift velocity. So we get E upon rho is equal to small e NE mu E capital E plus NH mu H capital E. E can be cancelled out from both sides and we get the reciprocal of resistivity 1 upon rho is equal to E NE mu E plus NH mu H. So this is the reciprocal of resistivity, and we know that the reciprocal of resistivity is actually equal to the conductivity. So sigma, that is the electrical conductivity that we were trying to find, is equal to the reciprocal of resistivity and is equal to E NE mu E plus NH mu H. This is the answer for required electrical conductivity. So conductivity in case of semiconductors depends on both charge carriers, electrons and holes, and it can be given by this relation. So that's all for the video. For further video, stay tuned and keep studying. Thank you.